California Institute of Technology in 1972 and taught at Princeton University and the Scripps Institution of Oceanography 1975 to 1984, before joining the Massachusetts Institute of Technology in 1984. He was head of MIT Department of Earth, Atmospheric and Planetary Sciences from 1988 to 1998. In 2000, he moved from MIT to SC, and in 2004, he was appointed as a USC University professor. As the director of the Southern California Earthquake Center from 2002 to 2017, Jordan coordinated an international research program in earthquake system science that involved over 1,000 scientists at more than 70 universities and research organizations. In 2006, he established the International Collaboratory for the Study of Earthquake Predictability, and since 2005 has been the lead SCAC investigator on projects to create and improve the time-dependent Uniform California Earthquake Rupture Forecast. Following the 2009 L'Aquila earthquake, he was appointed by the Italian government to chair the International Commission on Earthquake Forecasting for Civil Protection, which published a final report in Annals of Geophysics in 2011, proposing the deployment of operational earthquake forecasting. Today, Professor Jordan will present a work titled Crustal Structure of the Southern California Crust from Velocity and Attenuation Tomography. Thank you very much.
Thank you, Paula. It's an extreme pleasure to be here at INGV. It's been several years since I visited, but it's a fantastic institution. And I'm very honored to be part of what is an exceptional seminar program that Paula and our colleagues have put together. And thank you for the very nice introduction. As you get older, introductions like this are more like obituaries, but I've, of course, been around the block for a while. And as Paula mentioned, I was director of SCEC for 17 years. And during that time, helped to supervise a major program on using Southern California as a natural laboratory for the study of earthquakes, deformation, earth structure, and so forth. Today, what I'd like to do is focus on one aspect of that research, and that is the structure of the Southern California crust as we see it using both velocity and attenuation tomography. Now, this is a very big topic of which there has been many publications. I don't propose to do a review, but what I am going to do is look at the results from a series of papers that I've been involved in. Lee et al., which developed a tomographic model using full 3D tomography, published in 2014. A tomographic cluster analysis of that model done by Billy Eimold and myself in 2019. And then some work on attenuation tomography with Yu-Pin Lin, who is at the University of Taiwan. And she and I have developed attenuation tomography models for Southern California. So here's an example. This is the velocity tomography model known as CVM S4.26, derived by full 3D tomography. You can see a lot of interesting structure in this model. We're not going to look at these figures too long because we're going to look at the tectonic regionalization of this particular model. But the model itself is quite good. And in fact, as you can see from this slide, this shows in black seismograms recorded from an earthquake which occurred after the model was developed. And the red lines represent the synthetic seismograms using this model. And you can see that at low frequencies, and this is about 0.2 hertz and below, we see a pretty good match between the observed and the synthetic waveforms. And this model has been tested in various ways out to 1 hertz, and it's probably the best tomographic model we have in Southern California. So that's going to be one object of study. The second is this attenuation model showing the attenuation of P waves on the top, S waves on the bottom, and at different depth regions going laterally. What you can see immediately from this is that the P wave and the S wave attenuations look about the same. And one of the big themes in this talk is going to be why does the attenuation structure of P, or Q values for P and Q values for S, why are they almost equal? Another topic for this, our discussion, is the concept of tectonic regionalization. Tectonic regionalization approximates 3D structure by a set of domains, or a mosaic of domains, to each of which we have a characteristic crustal column. And it's an idealization that is predicated on Earth structure that has to be vertically correlated, has to be coherent across large regions. You have to have these regions separated by well-defined boundaries that you can recognize from the surface. Now, on a continental scale, when we look at cratons and platforms, orogenic belts, and so forth, this approximation can work pretty well. It has been very useful in seismology. But how useful is it on the smaller scale of Southern California? So we're going to look at the CVM S4.26 study area. This is also the same study area for the attenuation tomography to see what we can learn about how the velocity structure, which is derived completely independently of any knowledge of geologic provinces, boundaries, or anything, how well can we explain the structure by a tectonic regionalization. And our target here is to look at velocity profiles, both P wave and S wave velocity profiles. This particular slide shows you a velocity, about 15 velocity profiles. The points are shown on the map at the top. And you can see that there is a lot of variability in the upper crust, the mid crust, the lower crust, the MOHO discontinuity. And we want to use these velocity profiles as tectonic signatures. So the idea is to try to group the velocity profiles that are similar to each other into one pot and to ask whether that represents, corresponds with a tectonic region. And so in order to do that, what we use is a very simple machine learning algorithm. It's called the K-means algorithm. This is a particular version of it. What we use it to group velocity profiles, and the process is very simple. We decide how many groups we want. We have to specify that in advance. We just guess at what the centroids for those groups might look like. We take the individual data and we partition them we assign each profile to its closest centroid. We then, after all the assignments are made, we recompute the centroid and we iterate this process to convergence. Now, in this particular case, what you're looking at are 30 data points distributed in 2 dimensions. And we're looking at, in this case, partitioning into 3 groups. Here is the results for the velocity model CVM S4.26. And that has 1.5 million profiles, so the number of data. Those profiles are each represented by a velocity, a VS velocity profile and a VP velocity profile. Those each are represented by 100 numbers in depth, so it's a 200-dimensional space. And in this case, we're looking at the regionalization for seven regions. Now, I don't have time to go through the validation of this kind of analysis. We've looked very carefully. And one of the things we can see is that, first of all, the results of the regionalization do not depend upon where we start from. In other words, the seeding of the K-means algorithm. If you do it for P waves and do it separately for S waves, you get almost identical results. And moreover, as you increase K, going from small values to larger values, the the regionalization is very well behaved in the sense that it will typically take regions and partition those into say two regions, but without disturbing the overall structure of the model. So what you see here is a map which has the 7 regions colored in different colors and labeled with 2-letter designations such as GV and MD and so forth. And on the right, you see the velocity profiles that correspond to each of those regions. And these are the characteristic profiles for these tectonic regions. So let's take a look at this kind of a model. One of the things we see immediately is that we can associate these regions with major physiographic and tectonic provinces that are recognized at the surface. So for example, what we call CB, we associate with the continental borderlands, the California continental borderland. That's the offshore region. You can see that light blue is pretty much offshore. We have sedimentary basins that divide into 2 regions. One we label by GV because its primary association is with the Great Valley of California, a deep sedimentary basin. The other is labeled ST because it corresponds to the sedimentary basin of the Salton Trough. Now you can see that there's also secondary associations that make a lot of sense. So for example, for the Great Valley province, we also associate it with the Santa Maria and the Santa Barbara basins, and that we know geologically is a correct association. We also associate the sedimentary basins in the Los Angeles region with the Salton Trough rather than with the Great Valley. So these models make a lot of sense from what we know about from other structural information. Here's another pair of regions labeled MD for the Mojave Desert in orange and PT for the Proterozoic terrains of eastern California and Arizona. These are similar regions in the sense that they both represent extended continental crust. And finally, 2 regions associated with the batholithic terrains of California, the Sierra Nevada SN and the Peninsula Range batholith PR. And you'll notice that the secondary associations actually kind of mix these 2 things up. We see for the Sierra Nevada a dark green region to the west that corresponds to the PR region, and the SN region to the east. And that is something that we recognize geochemically and from structural geology. The geologists have divided the Sierra Nevada and Peninsula Range batholiths into 2 regions, a western region that's somewhat older and more oceanic in character, an eastern region which is younger and more continental in character. And it turns out that this batholithic dichotomy, which has been mapped by geologists, is well represented in this regionalization. And remember, the tomographic model knows nothing about the surface geology. And so this is all done without, and so it is discovering these features and the correspondence with what we know to be true is a big validation of the tectonic regionalization. So let's look at another way of validating. These white dashed lines represent boundaries between tectonic regions that we judge based upon our regionalization scheme to be pretty stable and robust in the regionalization. And so I've listed 13 of them, but I've also listed associated with those lines the surface features that we know. So many of these correspond to active or inactive faults, geochemical boundaries like in the Sierra Nevada, and also topographic fronts. I don't have time to kind of go through one by one, but I want to illustrate to you some examples. So let's look in the northern part of this region at lines 1, 2, 3, and 4. Line 1 is just the San Andreas Fault that separates the Great Valley from rocks to the west. Line number 2 is a major boundary that is buried by the Great Valley sediments, but corresponds to the transition from an ophiolitic complex into the Great Valley sequence. And that again is well mapped from using, for example, seismic refraction and reflection profiling. Number 3 is this boundary between the the eastern and western parts of the Sierra Nevada batholith. So the western part is associated with the Peninsula Range. The right part we call it associated with, we call it SN for the Sierra Nevada. But you'll notice that the data points that I plot on there correspond to the strontium isotopic ratios that have been mapped in this region. And the so-called 706 line that is the line that petrologists use to distinguish between the eastern and western batholith. That on the map corresponds to the difference between the white and blue colors on the left and the red colors on the right. So you can see that the tomography is actually picking up this, this dichotomy very, very nicely. Now this fourth line is a little bit more cryptic. What's going on there? It's kind of unusual because it's crossing into the, it's crossing into the Basin and Range and cross-cutting the northwest trending extensional features like Death Valley and Panamint Valley. So why is that a major boundary? Well, actually, if you look at the topography, what you can see is line 4 is a major topographic front, and it's also a big change in the Bouguer gravity anomaly associated with this crustal change, and represents geologists have mapped this as the early Permian boundary between the continent. And so this is an old structure, but one that is significant from the point of view of the velocity tomography. If we jump down into the Salt and Trough region, line number 6 is actually not associated with the active faulting, like the Imperial Fault that lies to the west. What it represents is a boundary between the Salt and Trough and the Proterozoic terrains that corresponds with the Algodones Altar Fault Zone system, which is pretty inactive now, but was in fact the boundary between Pacific and North America back in the Pliocene. And so again, another major paleo boundary. If we go to the Peninsula Range batholith, you can see that lines 8 represents the boundary between the pink rocks to the right, which represent the continental eastern zone, and the red rocks to the left, which correspond to the more oceanic western zone. And so that line makes a lot of sense, just as it did in Sierra Nevada. Line number 9 is a boundary between the Peninsula Range batholith and the structures of the LA region. In fact, corresponds to a fault called the Cristianitos Fault, which again was the major fault during the development of this structural separation between Los Angeles Basin region and the Peninsula Range batholith. So again and again, I could go through the others. These things typically coincide with major faults, topographic fronts, geochemical transitions that are mapped at the surface. And the boundaries are typically high-angle structures. They're fairly narrow structures. So they're separating regions that are relatively homogeneous from each other. And it's amazing that these features are discovered by tomography. So evidently the tectonic processes that have put together Southern California have developed these structures that are coherent over large regions, separated by well-defined boundaries, and these boundaries can be recognized at the surface. Now, one question we might ask is, what about the structure, the vertical structure? We expect on this scale, in this particular region, for those structures to be isostatically balanced. So we can test that. Here's a simple isostatic model where we have a 3-layer crust, an upper crust, a mid crust, and a lower crust. Separates, of course, the MOHO separates that from the mantle. And what we do is we take the velocities profiles for the specific tectonic regions. We average them over depth ranges associated with the upper, middle, and lower crust. So we get 3 different numbers there for P and for S. But we take the P velocity profiles and we relate them to density using Tom Broker's nonlinear relationship. And then if we look at what isostatic balance involves, we can see it's given by this lower equation, which relates the upper and mid crust density anomaly, the lower crustal density anomaly, including the effect of the MOHO, with the perturbation to the mantle density. And so if that equation is satisfied, we have isostatic balance. So let me make a plot of the different regions where we plot the on the horizontal axis, the upper and mid crust density anomaly, on the vertical axis, the lower crust density anomaly, including the MOHO. And so on this kind of a plot, the anti-diagonal line corresponds to complete crustal isostasy, meaning the mantle densities are the same. Deviations from that anti-diagonal correspond to small differences, or the differences in the mantle density. You can see from this plot that the points string out along that anti-diagonal with only small perturbations perpendicular to it. And what that indicates is that the isostasy is largely crustal. There are some mantle variations that are sort of predicted by this kind of an isostatic balance, and in several cases they correspond to what have been gravimetrically observed. For example, the Sierra Nevada has a positive density anomaly, small but significant, as shown on this diagram. So tectonic processes have produced an isostatically balanced crust, and that's not a surprise. We expect isostasy to be working, but it's interesting that you can recover that from the tomographic modeling. Moreover, the tomographic modeling tells you exactly how that isostasy develops. And so let's take an example. What you're seeing here is just the regionalization map with the 706 line that sort of gives you some idea of the distribution between continental and oceanic rocks. And it turns out that almost all of the rocks that have a continental affinity geochemically belong to either the SN region, the MD region, or the PT region. And when you look at the progression of those regions, what you see is a thinning and a density increase occurring as you go from Sierra Nevada, Mojave Desert to Proterozoic terrains. And so this corresponds very nicely to a model of the stretching of the Mojave and Proterozoic terrains that has been proposed by geologists, namely a stretching, a faulting of the sort that you see here, and then a mafic enrichment of the lower crust. So it's nice to, again, recover that from the tomographic model. Okay, let's make a transition now to the attenuation tomography. On the right is an average, a vertical average of the attenuation variation, and we plot that as a difference in a relative difference in the inverse quality factor, so the attenuation factor q to the -1. And what I've sketched on the map is sort of a kind of a simplified version of the tectonic regionalization. The black lines on the velocity regionalization on the left correspond to the ones that we were just looking at as major structural boundaries, and we've just sort of used those to come up with a sort of somewhat simpler regionalization map on the right-hand side. And what you can see is that the blue regions are regions of low attenuation, correspond to the batholithic provinces, whereas regions of high attenuation correspond to those provinces that have much more faulting and deformation. And we'll come back to that in a bit. So the data set for this particular model was pretty extensive for a Q model. One thing that I want to emphasize is that the P wave and Q wave and P wave and S wave attenuation modeling was done completely separately. So there's no crosstalk between the P wave modeling and the S wave modeling. And one of the things we're going to see is that even though they're done independently, they give essentially the same values of Q. Now, the way the model is set up is in terms of a mean 1D model, a three-dimensional relative variation in that equation shown in green, and a frequency dependence. So we know that Q is frequency dependent and has a power law dependence. we call the decay exponent associated with that power law alpha, and we have a value for both P waves and S waves. The way we estimate that value of alpha is to average over the lateral and vertical variations to get frequency variations. So we're in the data set we observe the spectral ratios in 10 bands going from 1 to 10 hertz. So this is looking at the high frequency attenuation. And what we get from the P wave inversions is shown in red, the red circles with the error bars. The S wave attenuation is shown in blue with the error bars. And you can see that the P wave attenuation is close to the S wave attenuation, slightly higher in terms of attenuation. So there's more attenuation occurring in P waves than in S waves. And that's a bit weird because we expect if the attenuation is due to anelastic dissipation, that the P wave attenuation should be about a factor of 2 lower than the S wave attenuation because the shear energy in a P wave is only about half of the shear energy in an S wave. And if the dissipation is occurring anelastically, that's going to be primarily by shear. And so the P wave ought to correspond to the dotted line shown in that frequency plot. But instead, we find much higher P wave attenuation. And what we're going to do is we're going to explain that difference by scattering. So the attenuation is a sum of two terms. One is the internal attenuation, or intrinsic attenuation as they call it, the internal friction, anelastic attenuation if you want to call it that. The second part is the scattering attenuation, which is very different because it's elastic scattering. The attenuation occurs because of interactions with heterogeneity. They essentially disperse the energy away from the waveform and decrease its amplitude. So rather than observing that the P wave attenuation is about 1/2 of the S wave attenuation, we observe that the two are about equal. In fact, this is a plot as a function of frequency. If you plot as a function of wave number, that actually moves the P waves closer to the S wave attenuation. So we have a hypothesis. The hypothesis is that in this high frequency band, 1 to 10 millihertz in Southern California, that the attenuation of both P waves and S waves is dominated by scattering, not by anelastic attenuation. And so let's look at that hypothesis. Well, first of all, let's look at the model itself. I showed you this plot before, but let's look at it more carefully. The upper, the upper row represents the P wave attenuation, the lower row S wave attenuation. Each panel is over a particular depth range going 0 to 4, 5 to 8, 9 to 16, 16 to 25. And what you observe is that, first of all, the S wave and P wave attenuations give essentially the same lateral variability. The colors here are on the same scale, and so you can see you have regions of dark blue associated with batholiths, you have regions of bright red associated with the faulted regions, and you get the same answer between P and S, even though the inversions were done completely independently. What you also see is that there are large coherent anomalies throughout the upper and middle crust, going from the surface down to the mid-crust at about 16 kilometers. And there is still variation in the lower part of the crust, but it's smaller in amplitude than in the upper part of the crust. And in fact, we've done lots of experiments, and it turns out that there is tomographic smearing that occurs between the upper crust and the lower crust. So that lower crustal signal actually could be a bias in the model associated with the smearing of upper crust into the lower crust. So it shows that here, just the model itself shows that the attenuation is lower, but that's probably biased high. It's probably even lower than shown in this diagram. Now, we can take that attenuation model, look at specific points within that model. The model is developed on a 20 kilometer square grid. Take each of the nodes of that and associate it with one of the tectonic regions that we have mapped from velocity tomography. And so that gives you the color scale there. But what we're looking at here is the correlation between QP and QS as a function of temperature in the mid-crust at about 10 kilometers depth. And what you can see is that there's essentially no correlation. There's a few red points that scatter high attenuation at high temperatures in the Salton Trough, but if you look at the average of the Salton Trough given by that red diamond, you see that there's basically no correlation with temperature. So if it were attenuation by inelastic attenuation, we would expect that to be strongly temperature dependent. We see no correlation with temperature, and that favors the scattering model. So here, in fact, are the data that give us insights into the type of attenuation. The first is that in all 4 dimensions, 3 spatial dimensions and frequency, QP is about equal to QS. And that is something that is simply explained by scattering, but cannot be explained by inelastic attenuation. There are models such as partial saturation of crustal rocks that can give rise to higher compressive attenuation and therefore can raise QP relative to QS. However, those mechanisms can only operate in the upper crust when you can have pores that have both fluids and gas in them, and those get closed up rapidly as you go to depth. So below 6 kilometers, that mechanism won't work. So the only real mechanism to explain the equality of attenuation is scattering. We also see that the P and QS variations don't correlate with temperature or, for that matter, with velocity. I didn't show you that, but they don't correlate with velocities either. The lateral variations do correlate with tectonic regions, with batholiths having low attenuation and faulted regions having high attenuation. And then the other point is that the attenuation variations are smaller in the lower crust than they are in the upper and mid crust. So the attenuation variations are stronger in the seismogenic zone than they are below the seismogenic zone. So we think these data support the scattering hypothesis because scattering can explain them, whereas inelastic attenuation can't. Well, let me show you how scattering can explain them. So we're using a particular scattering model called the Sato-Feller scattering model. This represents a full elastic first-order Born scattering theory. So we're looking at waves getting scattered out of the P&S wave, but not scattered back in. So it's just first order. And the scattering medium is assumed to be isotropic and to have a what's called a von Karman correlation function. And a picture of a solid that has a von Karman correlation function is shown there in the figure. It's characterized by an RMS amplitude of variability, which we call epsilon, a characteristic scale, A, and a fractal dimension, which we call D, and that's related to what is also known as the Hurst exponent, that's nu. So 4 minus nu is the fractal dimension. So we have those 3 parameters of the medium. We have one more parameter, and that's associated with what's called the forward scattering cutoff angle. The energy that's forward scattered doesn't cause attenuation. What it causes is the pulses to be moved. It can change the phase of the pulse, but it doesn't change the amplitude. So we have to be able to get rid of that energy. So there's a parameter in this model called psi sub c. It's the forward scattering cutoff angle. And it turns out that forward scattering cutoff angle determines the ratio of QP to QS, or QP to the minus 1 to QS to the minus 1. And we know that that ratio as a function of wave number is about unity, and that implies a scattering cutoff angle of about 40 degrees. And that's physically extremely reasonable based on other wave propagation considerations. So here's an example of the scattering model looking as a function of wave number, looking at q to the minus 1. The p waves are in red, the s waves are in blue. And this just shows you various parameters. As you vary with those parameters, what you get. You'll notice that in that inset diagram that psi sub c corresponding to 40 degrees gives you a QP-QS ratio of about 1. We also find this is our older data set, this is from the Lin and Jordan 2018 data set shown in the points, that constrains the slope along the high frequency side of an attenuation peak. That slope we can, in the Sato-Feller model, that slope is related. It essentially goes like, you can see that asymptotic relation in the upper right. It goes like A, the scale, times wave number to the minus 2 nu. And remember that we've already mapped that slope. We called it alpha. So in this notation, nu is alpha divided by 2. And we observe alphas between about 0.3 and 0.4. So that corresponds to fractal dimensions on the order of about 3.8. So high fractal dimension. The RMS variability in this particular model is about 8%. And again, the characteristic scale is about 10 kilometers. Now, what we've done is we've taken the new data set shown here, the points with the error bars, the blue and red, and we fit them to a model that actually includes inelastic attenuation. So what we're saying is that at high frequencies, scattering is dominating the attenuation, but we know at low frequencies that's probably not true. It's probably inelastic attenuation. So what we've done here is we've ginned up a broadband attenuation model that has two components, a scattering component shown by the dotted lines and an intrinsic attenuation inelastic model shown by the dashed lines. And what you see is, and then the total, the sum of those two, is given by the solid red and blue lines. And what you see is a peak in attenuation associated with the scattering. And that peak was first recognized by Keiaki. It's kind of sketched by him in a paper in 1980. It's since been confirmed in other regions, but this shows you the values for Southern California. And in this particular model, the RMS amplitude is about 7.5%. So there's a 7.5% variation in velocity. The characteristic scale for that variation is about 8 kilometers. The fractal dimension is about 3.8, 3.85 actually in this model. And QP is about equal to QS for scattering. That corresponds to a cutoff angle of about 40 degrees. The inelastic absorption band model is one that's developed to satisfy the low frequency attenuation that we see in surface waves and basin waves in Southern California. And you can see the parameters of that model there. Now, the implication of this is that the scattering between 1 hertz and 10 hertz dominates the attenuation. You can see that through this quantity called the seismic albedo, represented here by BP or BS. And when that is above 0.5, then scattering is dominated. You can see the scattering actually not only dominates between 1 and 10 hertz, but it actually is very important from 0.1 to 1 hertz. So even at low frequencies, scattering, according to this model, is playing a major role. Now, we can take this model and make a scattering model for Southern California that has lateral variability because if we fix the other parameters, it turns out that the epsilon, the RMS variability, can be directly related to the Q variability. So the relative variability in Q is equal to about twice the relative variation in epsilon, or say it the other way around. The RMS variability is about 1/2 the Q variability. And so what we can just do is we can take a Q model, such as the one shown on the right. This is again the depth average model. And we can just rescale it. And we can say, okay, this is all due to scattering. And we can satisfy the Q data, or the Q model, by simply varying the RMS amplitude. And we don't have to vary very much. It turns out that in the batholithic regions, we want to reduce Q by about 50%. So there's 50% plus or minus variations in Q. The batholithic region shown in blue would correspond to RMS variabilities on the order of 5%, whereas the high scattering region shown in red would correspond to velocity variations of about 10%. And that's exactly the range in which variability is observed in Southern California. So it's not an unreasonable model. Now, the scattering is stronger in the highly faulted regions than in these undeformed batholiths. I mean, we know the batholiths are fairly homogeneous structures. They have very low reflectivity. If you do reflection profiles across them, you get essentially no returns from the crust. And so the question is, okay, why is there differences between these regions? And the scattering hypothesis is due to the amplitude of the heterogeneity. And so why is the amplitude of the heterogeneity higher in the faulted regions than in the unfaulted regions? And part of that is no doubt due to the damage zones that are created by large earthquakes. If there was a recent study by Rodriguez Padilla and others in 2022 looking at the Northridge earthquake, showing that the damage zone, the volumetric damage associated with the Ridgecrest earthquake was much larger, much more extensive, with larger modulus drops than people had seen before. And so that's obviously a key process. I think it's also possible that there is a lot of heterogeneity being developed by essentially the interaction of distributed deformation, which is accommodated by viscous flow, with fracturing associated with frictional sliding. So there's an interaction between these two types of deformation in these regions. And models have been developed, sort of Fehring and Beal, for example, show that this can develop heterogeneity if you deform the region significantly. And it does a pretty good job of explaining why the variations are smaller in the lower crust than they are in the seismogenic zone, because in the lower crust, of course, frictional sliding is inhibited by higher yield strength, and viscous deformation is enhanced by the higher temperature. So that makes sense. Okay. Well, what I've talked about today really supports two hypotheses. The first is that this large-scale heterogeneity we can map tomographically can be approximated pretty well, about a 60-some-odd% variance reduction, by a discrete set of tectonic regions, each of which is characterized by an isostatically balanced lithospheric column and reflects the composition and tectonic history of the region. That's hypothesis number one. Hypothesis number two is that the attenuation of high-frequency PNS waves propagating through at least the upper crust, the seismogenic zone, is dominated by scattering from small-scale heterogeneities with high fractal dimension, not significantly by anelastic dissipation. And this latter hypothesis has lots of implications for ground motion studies. For example, in SCEC, we have something called the broadband platform that synthesizes broadband seismograms using two mechanisms. One at low frequencies, a deterministic simulation. At high frequencies, it requires stochastic simulation. So seismologists have known for a long time that there's sort of a barrier between about 0.5, 1 hertz, something like that, above which you can model waveforms coherently, below which, or at higher frequencies than that, you can't. You have to represent things stochastically. And these models suggest that perhaps it's that the fact that the scattering begins to dominate at about 0.5 hertz that is the reason why we have this transition, deterministic stochastic transition. Another important implication is that this may apply not just in Southern California, but to other parts of the crust. One of the things that we know is that in eastern North America, seismic waves travel much more efficiently than they do in California. And the classic explanation for that is that the crust is colder. Well, we would modify that to say the reason is because the crust is less heterogeneous, is more homogeneous in stable continental regions than it is in California. And what I show over there are the attenuation curves that have been developed by Atkinson and others for eastern North America. Those are shown in black compared to the ones we just discussed for Southern California. And of course, in Southern California, we see variations. And in fact, that lower blue dash dotted line represents the Sierra Nevada Peninsula Range attenuation that we get from our three-dimensional tomographic model. And you can see that it's pretty close to what you see in eastern North America. Eastern North America, you get the same slope, the same alpha that you have in California. And what that's telling you is that the fractal dimension is about the same, but the amplitude is much lower. And it doesn't take too much. It only takes about in this case, a decrease from 7.5% that we have as our mid-value for California to about 4% in order to explain those variations in Q. So I'm not going to read these main conclusions. I'll stop and open it up for discussion and questions. Thank you.
Thank you very much, Tom. I invite Andrea Morelli to conduct the discussion, please.
Yeah, very interesting, very impressive results. Thank you. So, are there questions from the audience here? Yes, Abigail.
I'm part of yours.
No, so people at home can hear your question.
Thank you, Tom. It was really interesting, your talk. I enjoyed very much. I have a couple of questions. One is related with the multiple lapse time window analysis. Have you ever tried to use it to get the seismic albedo and the extension length? And the second one is in your albedo calculations, I saw that P waves has the higher albedo than the S waves, so I was wondering what is the reason behind that. And another question is, you have the scattering attenuation in case of both P and S waves and their frequency dependence, because I haven't seen them, how they were changing respect to anelastic one. And the last one, I'm doing everything.
This is another seminar.
So the last one is have you ever tried to look at the Q anelastic and its frequency dependence in regions with the more fluids involved? How it was changing in your regionalization map? Because there are some areas.
How is the anelastic one changing?
Yeah, it's frequency dependence. Thank you. Sorry.
Okay, good questions. Your first question is very important, namely, what about, there's a type of analysis that seismologists do, which involves not only looking at the amplitude of the S wave, but also the coda of the S wave. And by looking at the coda, using a theory, a radiative transfer theory, you can actually separate out the intrinsic scattering, the elastic scattering from the intrinsic anelastic attenuation. So it allows you to actually separate the two out. The results that you get are completely inconsistent with what I've shown. So for example, in those studies, they've been done in Southern California and elsewhere, instead of getting a slope with frequency of about 0.3 to 0.4, they get a slope of about 1, which is inconsistent with our data. Secondly, at lower frequency, at about 1 hertz, let's say, the attenuation they get is much higher than we observe. So we get higher attenuation with a larger slope. We cannot explain the discrepancy. I have no specific explanation other than to suspect that there's some bias associated with the coda analysis. The coda analysis makes a lot of assumptions. For example, homogeneous medium, right? A scattering medium. And so what it doesn't do is it doesn't properly represent the scattering volume, which is of course has a lot of three-dimensional structure. So I'm not sure that what the explanation is, but the two are completely inconsistent, and the coda analysis is inconsistent with the results that we get from the scattering from the attenuation of P and S waves. Now your second question was, yeah, the albedo. Okay, so let's see if I go back just a few slides. I think I can do that. Yeah, well, let me go back one more here. Okay, so here's our broadband model. And the reason why the P wave albedo is different from the S wave albedo is shown by the slight divergence between the red dots and the blue dots. And so in this model, we fit the total attenuation by having both a scattering component and an anelastic component. And it's the anelastic component that gives us a slightly higher P wave albedo than S wave albedo. So if it were just scattering, that would correspond to those little dotted lines. The albedos would be the same. But they're not because of that slight divergence. Now, is that divergence observationally well constrained? I would say not too well constrained, but to the extent it seems to work in the sense that it's consistent with this broadband model, at least we have a consistent result. Okay, I know there are two more questions and I can't remember what they were, but
So the frequency dependence of this cube S and
the frequency dependent.
in the case of the scattering attenuation.
Well, I'm sorry. The frequency dependent or lateral dependence.
Frequency dependence is coefficient n, FAR n.
So you can see this from the scattering model. In our notation, we call that nu, or the Hurst exponent nu. That Hurst exponent is equal to alpha divided by 2. So by observing alpha, which we can do, we can estimate that Hurst exponent. And the values we get are about 0.15. All right, so the fractal dimension is 4 minus the Hurst exponent, so that gives you a fractal dimension of about 3.85. So it's very high fractal dimension. People have looked at well bores and other information, high frequency reflection information and so forth, and they find high fractal dimensions of that same order. So that seems to be okay.
Okay, last question was related with the fluids contents in different regions that you had in the regionalization map. And I was asking whether if you try to look at the frequency dependence in that region, where the fluids...
Well, we look at the frequency dependent, you mean in the uppermost crust? So generally your question is about the role of fluids. And of course we know there are fluids in the crust. If those fluids partially saturate the pore space within the rock, you can increase the compressive dissipation. And so people have used that as an explanation for why QP is so high, or why QP to the -1, the attenuation of P is so high. That mechanism works fine in a petroleum reservoir, for example, at shallow depths. It works fine in the laboratory if you simulate in the laboratory. It does not work fine over the crust as a whole, because by the time you get to 5 or 6 kilometers, the rocks have essentially closed up. You can't support a gas phase in the pores, and the percolation threshold, the porosity drops below the percolation threshold. So we don't think that those models can explain what we see throughout the crust.
Because we know that in the dry, for example, in the laboratories, if you have the dry sample, it seems that Q is not frequency dependence, but when you start injection fluids, it gets more frequency dependence. So I was asking if you are seeing in your data this kind of variation.
I'm not exactly sure what kind of frequency dependence you get in the laboratory. I know there have been extensive laboratory experiments, but I don't know how those scale into the scale of frequencies that we're looking at from 1 to 10 hertz. So I don't know how to answer your question.
Okay, thank you.
There is another question that was asked from remotely that I just read. This is from Enrique Roisenberg. Professor Jordan, thank you for your insightful lecture, and I have a question regarding the interpretation of Q values concerning anelastic attenuation versus scattering. I noticed that despite Q values show no correlation with temperature, zones with higher fault density and fluid content exhibit greater attenuation compared to batholiths. Given this, aren't faults and fluids typically associated with intrinsic attenuation? Could you clarify why these observations are attributed to scattering rather than intrinsic attenuation?
Again, it's essentially the same discussion we were just having about the role of fluids. Clearly, fluids do play a role in the crust. They can be part of the anelastic scattering mechanism. However, they cannot. So if you have the fluids in pore spaces without a gas phase, then the QP should be QP to the -1. The P wave attenuation should be lower than the S wave attenuation. That's what the laboratory experiments show. So in the very upper crust, where you can have a gas phase in the pores, so you get partial fluid saturation, you can explain the ratio of QP and QS, but that mechanism does not work below something like 5 or 6 kilometers for the reasons I mentioned.
Other questions here? Luca.
Great talk, first of all. I'm not sure I understood everything you explained, so forgive me if I ask something stupid. So you have the same resolution between area of higher 1/q and area lower 1/q? Because basically what I saw in a simple 2D tomography, the area of low attenuation, they could have any kind of numbers. You didn't see any difference in the results. And all the results were driven by the area of high attenuation. That's one question. And I saw the comparison with Atkinson results and talking about ground motion, but don't they mix everything in their results? So I don't understand what is the conclusions about the scattering and everything, and the similarity with the Atkinson Eastern North American result. They probably, I'm not sure what kind of results are them, but I think they were using ground motion, strong motion stuff, so they probably are mixing everything.
Okay, I'm not sure I understood your first question, where you said it was being driven by the high attenuation regions.
Yeah, I mean, if you have your energy that gets dissipated away, it gets dissipated away in the area of low Q, high attenuation, and the other areas doesn't really matter what kind of Q they have. If they are down here or maybe much lower.
Well,
can you make?
We have lots of paths that are crossing just the low Q regions, the high the high Q regions, the low attenuation regions, such as Sierra Peninsula Range and so forth, and those seem. I mean, I think we can measure the Q for those regions, but look at this plot here. The Sierra Nevada, which is, and then the Peninsula Range Bathurst, which are the two low Q, high Q, low attenuation regions, shown by that dashed dotted line. That's what our model shows. And look at how that compares with Eastern North America, which has even lower attenuation. Notice that the slope in Eastern North America is the same as the slope that we find in California, and the values are comparable, maybe a little bit lower attenuation in Eastern North America, but the Sierra Nevada is close to that. So, I think there's a consistency that we see for the low attenuating regions that suggests that it's just less scattering.
Thank you.
Maybe we can take the question by Claudio. There's a microphone coming.
Hi, nice talk, Tom. So I have a question about the distribution of data with distance. and so the relative sampling between the upper and the lower crust.
Yeah, sorry, I wasn't able to show in detail the tomographic results, but if you look at the ray path density as a function of depth, what you find is that there's a high ray path density with a peak at about 10 kilometers. In the mid-crust, the ray path density drops somewhat lower, but peaks up again in the lower crust. This, of course, having to do with the distribution of stations and earthquakes. So I guess the way I put it is that our resolution in the lower crust is probably less than in the upper crust. And in fact, the tomography will tend to smear the signal from the upper crust into the lower crust. And we think that partially explains why there's a tremendous vertical correlation. What you see in the upper crust is what you see in the lower crust in terms of the lateral variability. But that may be due to the smearing of structure into the lower crust. So I think basically, I think what our results say is that there's a lot of variability and attenuation in the upper and mid crust, less variability in the lower crust, and we're probably even overestimating that in the lower crust because of the smearing bias.
I also have a question actually on the velocity tomography. So we'll change topic a little bit. I like very much the regionalization approach that you followed. And it's essentially some sort of low-dimensional model space projection of your tomographic model. You, of course, showed that K equals 7, I mean, 7 clusters make a lot of sense. But I wonder if there is some sort of statistical test based, I don't know, on information theory or something that can show you what is the optimal number.
Yeah, I get into a discussion I didn't have. In fact, I had 2 slides about this in the talk, and when we went to project them, because we transferred from a Mac to Windows, it screwed up those 2 slides, so I eliminated them, so I'm sorry. But we have done a lot of testing of the regionalization, and in particular, looking at, so K is the number of regions, and we've looked at K going from 1 to 10. And what you find is that a very systematic refinement of the model in a very stable way, up to about K equals 7. When you go above K equals 7, and so below K equals 7, for example, you get the same results if you just use the S waves or just use the P waves. And the ones I showed you, it was actually a combination of the 2 just to combine the data. But so it doesn't depend on whether it's P or S waves, you get the same answer. Also, it doesn't depend on the seeding of the machine learning algorithm. So whether you do supervised or unsupervised seeding doesn't matter. So we think we're at a global minimum. But when we go above K equals 7, the S wave and P wave results diverge, and we have statistical measures of that. So we think that the K equals 7 regionalization is the most informative. If you go to higher regionalizations, you see some interest. What happens as you go to higher and higher regionalization, it will take a given region and divide it into, let's say, 2 parts without changing the rest of the regionalization. So it's very stably behaved. So I think the regionalization is very robust.
Can I actually have a follow-up? It's actually great that from tomography you essentially find geology, because you find, but I wonder whether so essentially you find geology as a posteriori, but I wonder if there is a way, or you ever thought about using geology as an a priori in this sort of exercise.
Yeah, I haven't done that, and I don't think it's a very good idea, but the USGS has. And the USGS, for example, in the so-called San Francisco Bay Area model, is based upon a geologic, it's not just 2-dimensional and tectonic regions, but 3-dimensional construction of geologic units. And then from that, they attach to those geologic units velocities, and that gives them a 3-dimensional model. Now, that model has not been properly tested, so I don't know how good the performance is. But yeah, I'm not sure how that would work.
So I think that we are done with the time. Thank you, Tom, again.
Okay, I invite Alessio Piatanesi to present Professor Thorne Lay.
So, good morning, everyone, and thank you for coming. It's a pleasure to me to introduce Professor Thorne Lay. I'm actually pretty sure that many of you already know Thorne by its reputation, and it is also likely that some of you have studied the fundamentals of seismology using the popular book by Lay and Wallace, Global Modern Seismology, as I did in the past. Thorne Lay completed his undergraduate degree in geomechanics at the University of Rochester in 1978, and then arrived at the Caltech Seismolab in the same year. Here, he completed both the master degree in 1980 and the PhD in 1983. After a period at the University of Michigan, Thorne Lay joined the faculty at the University of California in Santa Cruz in 1990, where he taught continuously and where now has the role of Professor Emeritus. Thorne Lay is the recipient of a very large number of awards in recognition of his research, teaching, and service in seismology and geophysics. These awards are obviously too many to be listed, but I want to mention just a few. The Gutenberg Lecture of a Seismology section of the American Geophysical Union in 2011, the Reed Medal of the Seismological Society of America in 2014, and the elected member of the National Academy of Science in the same year. One of the main research interests of Thorne Lay is the use of seismic wave recordings and modeling to indicate the structure of the Earth. Particularly relevant are its works on imaging structures associated with internal dynamics of the mantle and the core mantle boundary. Another important research program has involved analysis of signals from underground nuclear explosions for the purpose of characterizing the yields, the burial depth, and the source process of such events in view and in support of nuclear testing agreements. A third broader research program of Thorne Lay is on earthquake-related investigations that include waveforms modeling of body surface waves to develop seismic models for the entire rupture process. And a few years ago, some INGV researchers have started a collaboration with Thorne to study the source of large tsunamigenic earthquakes. And today, Thorne, in his presentation, will give us an overview of such studies, and in particular of the use of tsunami observations for resolving coseismic slip of recent and historical large submarine earthquakes. So now I would like to invite Thorne to join the stage and to give us the talk. Please, Thorne.
Well, thank you for my obituary, Alessio. I appreciate that. It's a pleasure to come and to participate in the 25th anniversary celebration, kind of the formalization of INGV. Over the years, it's been great to watch the emergence of stronger and stronger research program in seismology and earthquake and tsunami modeling, and now monitoring, and the increasing missions that INGV is being given to monitor volcanoes and everything in the Mediterranean. And to come and visit and see it has been gratifying. I was very lucky that the timing of this talk allowed me to participate in the workshop on landslide-induced tsunamis that was held at Stromboli for the past few days, which is a fantastic research venue, but with all the complicated logistics, we had a wonderful field trip. Everything worked out amazingly well, and the INGV staff was superior in making it all happen. So I really applaud that effort, and the very dense and informative conference that we had taught me a tremendous amount. I had not worked myself much on landslides, only a few events. And I learned a lot about the modeling capabilities and came to appreciate the advanced skills that INGV has developed in terms of such modeling, and the hazard response that they have to do, like within 3 or 4 minutes on Stromboli to give tsunami warning. It's requiring very sophisticated multidisciplinary strategies, and it was fascinating to watch how advanced that has become very quickly. But during the course of the workshop, I mean, naturally, the portrayal of tsunamis was that they're kind of bad, right? You know, they're dangerous, and they do damage, and they hurt people. I'm going to try and emphasize that tsunamis are our friends at some times. They can be a bully, but they can also be a good friend to people that are trying to characterize earthquake rupture properties, because they're an additional type of wave generated by the source that we can analyze, perhaps jointly with seismic waves, with geodetic observations, with other constraints to characterize large ruptures. And in that sense, they can be very valuable. The review paper that I produced for this conference, for the special issue that will celebrate the 25th anniversary, is identifies just recent examples of the last 5 years or so of applications of tsunami in the joint analysis to determine complexity of earthquake ruptures. And it's a testimonial to how diverse the applications have been and how valuable they've been, because tsunamis are providing unique information. And that's what I'll try to convey in my talk here, that in their friendly aspects, tsunamis can be very beneficial, even if they are, you know, a dangerous phenomenon. It's also notable, I have never given a talk where the conference paper associated with was actually published before the talk. It's amazing. I really applaud Annals Geophysics. It's very impressive, very efficient, and a pleasure to have worked with the people there, because unlike many journals now, which are very slow, it lived up to its expectations and its deadlines amazingly well. Okay, so I begin with just a very traditional depiction of what we've been kind of pretty confident about for the past 15 or 20 years, which is that the incorporation of tsunami observations into imaging of earthquake sources through finite fault inversions adds critical, valuable information. And I depict this not with actual data, but with a simulation of synthetic data. It was designed for the 2010 Maui earthquake, a magnitude 8.8 earthquake in central Chile. And what we show here is called a checkerboard test, in which we prescribe over the fault model that we're actually using to image the slip based on the available data recorded for that event. We demonstrate the value of each type of data set by constructing a forward calculation with a alternating pattern of positive slip, complicated checkerboard, constructing for multiple data types, for teleseismic waves, for regional recordings that we have. They may be GNSS statics or high rate GNSS, for INSAR observations, and in this case for tsunami observations from just 4 dart buoys offshore in the Pacific. And you make the forward calculation for the alternating pattern. You have a data set, and you invert it to see how much you can recover that pattern based on any one type of data. For example, this would be the data from, there's just a handful of high-rate GPS stations, but it's powerful because it's a mix of seismic and static information. And you invert, and you see, well, does this look like the known model that the synthetics were calculated for? And it will be imperfect, and it'll be imperfect because of the data coverage, how many the stations are, and the intrinsic nature of the wave or the field that you're using to characterize the source. And you can recover some areas where the stations are right in here, so they do pretty good, but they're going to do poorly in other areas that are more remote and don't have local stations. Over here is for the teleseismic data, which is seen at all azimuths, but it's downgoing and it doesn't give high resolution, and you get some of the checkerboard, but you have very poor recovery on the margins, not too surprising. From the INSAR, which is pretty much a continuous deformation field that could be observed, and campaign GPS, I think there were 80 sites had been repeatedly measured, and we made the calculation for all of them. You recover very well the on-land pattern of slip, but you do very poorly offshore. That's not surprising. The INSAR tells you nothing about the offshore. And the GPS has limited resolution that diminishes with distance from the coast. Here's with the tsunamis, it's the opposite story, where there were just 4 stations, tsunami gauges. Inverting those data, we can do the offshore part of the pattern and you recover it well. And of course, you do very poorly on land. There's no information of tsunami from the on land. So what has been done by multiple groups, and this is work that I involved in 10 years ago, but it goes back to 2004 Mandache earthquake, where I began to get involved in using the tsunami to characterize the sources. If you put the data together and you do it in a way that weights the value of each type of data set appropriately so that you don't kind of overemphasize or underemphasize them, you can obtain a model that recovers with good fidelity the input slip distribution. This kind of gives us some confidence that it's useful to add the tsunami because this high resolution of the offshore is not provided by any of the other types of data. It's really the only way to give detailed resolution offshore. Okay, so let's see some recent applications. Now, in the paper, as I said, there's over a dozen examples of recent studies, and there have been 2 prior review papers that I've worked on in 5 years ago, 10 years ago, with the group here in INGV that have characterized this development over the past 15 years. So there's many examples that you can look at to see how the data have been useful. Now I'm going to show it for 2 events along. This is the Alaska Aleutian Subduction Zone, Alaskan Peninsula here. And recently there was a large events in 2020 and 2021. And I'm going to spend the first 10 minutes or so to explain how the tsunami benefited us in the study of these large megathrust earthquakes. They're on the plate boundary, Pacific plate under thrusting the Alaska Peninsula. There had not been a big earthquake in the area of the 2020 region that had been called the Shumagan Gap. In this region of the 2021 earthquake, the last large earthquake was in 1938, so we don't have very good data for it. And the existing models, another talk I could tell you, the existing models are largely wrong. Okay, so what is interesting about this region, or unique about it, relative to the other studies that I've worked on with Fabrizio and Stefano for the last 15 years, is a very flat continental shelf offshore. This is continental material, and the subduction zone has a flat, very shallow continental shelf, only 200 meters or less deep water. And so when you have earthquake on the plate boundary, if it's down deep in the 15 to 40 kilometer depth range, typical of megathrust faulting, it's under very flat continental shelf. That will produce long period tsunami under thin water layer. Whatever uplift occurs, it will be very long wavelength. Only if the slip goes out to under the continental slope, beyond the break where you get deeper water, then you can generate higher frequency tsunami. It's what I learned mostly from the study of these events was how nonlinearly abrupt that is. That if you confine slip and uplift to under the continental shelf, you will get very different tsunami than if you have any uplift at all out on the continental slope. And this gives you high precision resolution of the up-dip limit of slip, which is one of the most challenging things to resolve in the finite fault models, because the geodetic data, the seismic data on land, and the INSAR data do not constrain the up-dip limit of the slip. You're getting further away, as we saw in the checkerboard example. So the reason this area is particularly interesting is that the NOAA has deployed dart buoys offshore, and these, since 2004, the embarrassment of most of them not being operational in 2004, they've been fairly well sustained, and they produced available data for the past 20 years for most of the earthquakes around the Pacific, but they're very close and well positioned just offshore of the Alaskan Peninsula to provide nice deep water tsunami observations that we can incorporate into the analysis. Now, there are tide gauges along Alaska and the coast of Canada and the US that we can use, and also in Hawaii, and we will use them. But the deep water tide gauge from DART stations is much easier to model robustly than the complicated shallow water environment around tide gauges. So I understand there's going to be 2 new gauges in the Mediterranean that INGV is deploying. This is fantastic. The first 2 Mediterranean dart buoys. I hope it will grow to be 20 or so, covering the Mediterranean over time. Well, I've got several students over the years that have worked on finite fault models, and they tend to kind of work independently. They've gone off, they have their own programs. And so we often produce competing models within my own group, or my legacy of groups. And 2 were rapidly produced, which did not use the tsunami data at all. They used the rapidly available seismic data, the available GPS data, the regional strong motion stations, regional broadband stations, and INSAR data in various combinations. And so there's 2 studies that did standard finite fault inversion, which are now pretty routine. They're practiced routinely for magnitude 7.5 and larger earthquakes by the USGS, for example, and they produce them and post them online. This is one study that used just teleseismic and the regional GPS data. This is another study that used teleseismic, regional seismic, INSAR, and GPS data. It was a more complete data set. This is for the 2020 event that was in the Shumagon Gap and kind of filled the gap. It will no longer be called a gap, I suppose. And they recover models that are essentially slightly different. These are different methods. This is a least squares inversion program. This is a simulated annealing program. They recover slightly different slip distributions, and so it's a non-unique problem because it depends on the data set, depends on the configuration, depends on the algorithm they use to get the slip model. Okay, so you have 2 models that fit their own data sets very well. What you want to do then is have some independent information that helps to discriminate the strengths or weaknesses of these models and to reinforce what you can trust. Try and narrow down the non-uniqueness of the ensemble of models that are produced. It's probably 10 models produced with similar data have been published by now. Okay? Well, the approach that we use is to exploit tsunami observations, to go and look at those recordings from the dart buoys and see how they do. And anticipating how that might differ for these 2 models, if you take this model, you can compute the seafloor deformation, and the red areas are uplift, so that's going to push up the ocean water and excite tsunami. The same for this model. You can see that this model, all of the uplift is under the continental shelf before you get to the break. Okay? It will generate very long wavelength tsunami. This model, even though it was independent how they defined the extent of their fault model, puts some slip that puts uplift that goes beyond the break onto the continental slope. And that will excite shorter period and larger amplitude tsunami energy. So that's shown on the left. This is the calculation of the tsunami peak amplitudes. And you see you get fairly weak peak amplitudes, especially all the way to Hawaii, from the model where all the continental slip, or all the slips on the continental shelf. When the tsunami, this long wavelength tsunami is excited there, as it goes off to deep water, it de-shoals, it gets weaker, okay? So it gets a very weak far-field tsunami. Because of this a little amount of slip, and it's not much slip, but there is uplift out on the continental slope, the tsunami here, you can see, these are on the same scale. You get a much stronger tsunami excitation going into the Pacific, and particularly a stronger wave hitting Hawaii. And that's for 2 models that fit very well the same or intersecting data sets of seismic and geodetic observations. Okay, well, if you recognize that these waves going toward the ocean are going to pass various dart buoys as well as go to nearby tide gauges, These are the DART observations. This is for the model that all the slip was under the continental shelf. And you can say, well, it doesn't do too bad. The wave, the first arrival is a little bit long period, too much long period, a little bit low amplitude, and you see that in almost every case, and a little bit late. First peak is a little bit late. Okay, so it's not bad though. You know, if you were just using it to validate them, I say, well, it's okay. And that's in fact what they did in that paper, showed this synthetics. For the model that was produced, the other model that had more slip out beyond the shelf break, you can see, wow, you suddenly peak up a big first pulse that's now a little bit too early, and it's bigger than the data. Yeah? It's a subtle thing, and the slip model's the same peak slip, but just small shifts of 20-kilometer difference placement of the slip puts some slip out onto the continental slope. It is truly a nonlinear enhancement as a function of small differences in the position at which the slip occurs. So what we try to do then is exploit the recognition. The main problem with these models, or the main issue, is how far seaward they extend. Now there's various ways that we could deal with this problem. We could quit, I guess. I'm not getting an advance. Can you manually advance it? I'm not getting a... I mean, the strategies at this point, you could try to put the waveforms into a joint inversion. And this is what we've done even in the Maui earthquake, do a joint inversion of all the data sets. Or you can recognize that the one deficiency or the one sensitivity is how far seaward the slip model goes. It could be, yeah, I don't know. Okay, they're looking for batteries for the. But let me just discuss what we will see. You have two choices here. One is to do a joint inversion. You could just put the tsunami waveforms in, and you have to calculate the Green's functions from all the positions on the fault model, just like you would do for the seismic and geodetic data, and do an inversion. There's a bit of a problem here in that the earthquake is right under islands. So there's very shallow water zones in the overlying islands above the large slip zone. So the calculation for the tsunami Green's functions becomes nonlinear. It's amplitude dependent. It depends on how strong the slip is. You cannot treat it as linear. So you can get around that problem using larger grids and other things to stabilize the nonlinearity. What we will do is to simply modify the grid. Don't allow it to go as far seaward when you know that if it goes seaward, it puts too much, any slip will be too much slip. So we prevent that, we exclude it by specifying that you have like zero displacement in the shallowest row of the model. And then you do the calculation with that model, produce the tsunamis, compare them with the data, and see if you can converge to a well, pointer wasn't really the issue.
Just this pointer.
Yeah, no, I mean, the pointer was actually working, so maybe it just got used up. Oh, okay. But then Will you advance it for me then? Okay. Now we can continue. This is just showing the faraway tide gauge stations, notably those in Hawaii. This is very weak. Okay, for the top 3 rows are for the model with slip all under the continental shelf. The lower 3 are for a model with slip that goes beyond that. And you see at Hawaii, which is the bottom 2 in each of the panels, that when you get any slip out under the continental slope, boom, you get high frequency tsunami, and it violates the data, okay? So you know it cannot slip that far. So in the next slide, what we have done is to find a model by basically invoking zero slip in the shallow rows and doing that row by row, doing many different, 5 different reductions of the size of the model, redoing the seismic and geodetic conversion, fits the data the same. Those data have this is all in the null space of them. They do not really resolve that slip far offshore, and they'll put it elsewhere in the model if they need slip. So you get the same fit, but now we have a model that when you calculate the seafloor uplift, it's all under the continental shelf, and if it produces something intermediate between those 2 models. The next slide will show that when we calculate the slip, or calculate the DART recordings, now the waveform fits are very good. We no longer are over-predicting with too high a frequency and big amplitude a wave that was resulting from going beyond the continental break. The slope break, we have good timing, good amplitude, good frequency. So it's in between the 2 models, but it's a better constrained model. And it's incorporated the tsunami observations. That provided this constraint on the up-dip extent of slip. And it's within 1 grid subfault dimension. So within 10 to 15 kilometer resolution, we know where the up-dip limit of slip is. Now it's for the up-dip limit of tsunami-genic slip, which is more than a ½ meter in this case. So we know the slip, there could be weaker slip going further seaward than in this case. Thank you. But I really don't even care because that's always poorly resolved. Okay, so the model does have kind of slip right to the edge of the model, and that's a little bit disconcerting for us finite fault people. We'd like the slip to naturally taper. It ends rather abruptly, but I'm going to come back to show that that's actually probably reasonable. We can then take a model where we believe the slip distribution is now well resolved along dip. We can compare it with the distribution of aftershocks. They concentrate. There's some going slightly seaward of our model, but that's typical that the aftershocks will surround areas of large slips. So there is some seismogenic potential of this shallower interface, but we have confidence that the large slip is well resolved. Let me turn to the 2021 earthquake. It's going to be the same story, so I can do it more quickly. This event, also a thrust event just to the north in what's the 1938 rupture zone. This is the aftershock zone that's been drawn for 1938. This earthquake is an 8.2 thrust event on the megathrust. And same story, groups do inversions of seismic and geodetic data. This is an example. Starting model has a very big data set, doesn't have islands on top of it, doesn't have quite as proximate or close by GPS, but it's very well resolved and it's a bigger earthquake. This is a typical model that was, it has some slip going out, because you give a generous fault plane, it puts some slip shallow that produces uplift that goes out beyond the shelf edge. Well, that's going to present problem. And ultimately, after we model the tsunami it predicts is shown over here. This is the peak amplitude tsunami. It's a strong wave going out to the ocean. It's going to violate the data. We end up perturbing that model by eliminating these kind of low slip rows, imposing zero slip in them, forcing the model to contract back away from the shelf edge, get a model that fits the GPS and seismic equally well. There's really no difference in the variance between these models. The uplift is now contained within the shelf region, and it produces much weaker tsunami. It's amazingly strong for just perturbing small amounts of slip. There wasn't like a huge amount of slip. There might have been 2 or 3 meters of slip going beyond the margins of the model that we have curtailed. On the left is shown the data for the Starting one, you can see the amplitudes are too early, too big. The red is the synthetic. You can see we're really violating it, particularly bad at tide gauge stations in Hawaii. The model where we've adjusted based on tsunami by taking row after row until we get an optimal fit. We now fit the amplitude, the timing, the period of the main tsunami arrivals, and we don't have these violations in Hawaii. We're not exciting the very short period tsunami that goes to Hawaii. Okay? So just as in the checkerboard case, we're getting good information about where the slip is, but in this case, we're actually being able to put a bound on how seaward the slip goes based on tsunami. It's not available from any other information at this point. So that's why I say it's our friend, because it has given us a powerful constraint. You can do the same analysis of the slip distribution relative to aftershocks. And here, there's a lot of aftershocks in the shallow region. It's not as though there can be no slip there, but there was no significant coseismic slip larger than ½ meter, or else we would see it, because it's a very efficient exciter of short period tsunami, which we did not observe. But still, these models end very abruptly. It's bothersome to us. So we compared the position of the faulting and where the slip occurs with independent information about the megathrust interface, which has been obtained by seismic reflection work. And there are multiple seismic reflection profiles that have been done in this area. With a long streamer, they see down to 25 kilometer depth with high resolution. And if this one here, line 3, is right through the middle of the 2021 earthquake, where all the blue aftershocks are shown. And our fault model starts at 25 kilometers. Initially it had gone way up here. We cut it back to 25 kilometer depth in order to suppress excitation of the short period tsunami. And it's at 25. And that is right in an interesting spot. The reflection imaging in the blue dots shows a very sharp, kind of rugose, or a slightly rough interface, but a single sharp reflector down to 25 kilometers depth. At 25 kilometers depth, it turns into a shear band that is about 2 kilometers wide. And our fault model is right within that shear band. It's along the upper layer of that shear band. And this has got strong multiple reflections from it. So we think it's cumulative of many slip surfaces that have done damage in this region. And this is the most recently activated fault through this. But the abrupt end is where you transition between single interface to this shear zone. So dynamically, the rupture is coming from below. It comes up into this area where there's only one rough, sharp boundary at shallower depth, and it stops the rupture. So I think the abruptness of the transition from 2 or 3 meters of slip to 0 is happening right where the transition and the reflectivity is suggesting. Very similar thing along, say, line 5, which is through the 2020 event. The reflectors come down to 25 kilometers, and then it splits into about a 3 kilometer wide parallel set of reflections. So there's an abrupt change in the interface as well in that region. So this is an explanation for why the rupture doesn't kind of extend to shallower depth gracefully, because otherwise, you kind of would expect that if you have 2 meters of slip, it's going to go to 1 meter and then ½ meter. It doesn't do that, but because it's probably being disrupted by the roughness of the interface. Okay. So that's 2 of the stories. I'm going to tell 2 more stories. One is for a classic earthquake along the same region, the Aleutians Islands. It's a 1957 earthquake that's going to rupture along here. It's the longest earthquake that we've observed. It has about 1,100 kilometer long aftershock zone. That's outlined here in kind of pinkish color. The dots indicate the results of a relocation of all these 1957 aftershocks, and it's still equally long. It's been estimated to be an 8.6 to 8.8 earthquake, which is next to only the 1964 Alaska earthquake in size. Okay, so this is a famous earthquake, but it's in 1957. And we're going to see the tsunami data totally changes the story from what we had available. That's what I would tell you. The earthquake had been studied by some famous seismologists and famous tsunami modelers, and what they had found was that the data are miserable. There's only 5 on-scale seismic records that they could collect from around the world in 1957. So they have a real dearth of data. And there are a handful, 6 tide gauge recordings. Of course, there's no DART, there's no GPS, there's no INSAR. So very limited data for such a great earthquake. Seismic data analysis had been done, some characterization of the moment rate function indicating, yeah, it ruptured for a long time. It's a big earthquake, no question about that. Only one attempt to infer finite fault from that had been done from one record. And it was using surface waves that went opposite directions around the world, made R3 and R4 arrivals. And this was inverted into a slip distribution that put all the slip in the western part of the 1,100 kilometer long fault zone. Zero slip, actually negative slip in the eastern part, but it was noise. So, very strange. The tsunami modeling also put all of the slip in the western part of 1,100 kilometer long fault. So it's strange, you have an 8.8 earthquake, 1,100 kilometers long, and all of the significant slip from the available seismic and tsunami observations was in the western 500 kilometers of the fault. This is where we were at. This was work done by Johnson and Satake's papers, and then collaboration with Larry Ruff and then Sykes. Well, it's always bothered me, this event, but I knew that there wasn't much data for it. Fortunately, a surprising group came to the rescue. They took these, they knew this model. This was the model from the tsunami. This was the model from the seismic. And you have all this 700 kilometers of the fault with no slip. There were some aftershocks, but like 5. So was it really overestimated that there just were a few aftershocks, or did the earthquake really generate slip out there? Well, the group that came to the rescue, I say they're unusual, but I don't mean to offend anybody, was geologists. Geologists went to the islands. They went to the Aleutians finally, 20 years after Johnson and Satake's paper. In 2016, Rob Witter, they went and they looked at islands along the eastern part of the rupture, and they saw huge inundations along these islands. This particular one's at Stardust Bay on Sadanka Islands on the eastern end. And there's a nice bay, and they saw run-up along here that goes up 32 meters, okay? Substantial. And it left at the top of the run-up a rack zone with big trees, big washed-up trees that are way above the normal storm level. So these are not storm deposits, and there are no trees on the islands, so they were not local collapses or anything. They were brought in, and you could date them, this is 1957. Okay, so in 1957, in Sadanka, in the eastern Aleutians, had 32-meter run-up. That will not be explained by the models that were available. Nikolsky and others, they took those observations, they made some preliminary calculations of what type of tsunami it would take in order to make the sea wave that big. And you need, in this region here, what had been called the Unalaska Gap, 20 meters of slip in 1957. So its designation as a gap was because they did not recognize that this had happened. There was recent big slip in this region in order to account for this tsunami. Now, perhaps it was a landslide tsunami or something you might be thinking. What you can argue, though, is you go to the next island to the west, to Umnak. You find a nice bay, and it has like 20 meters of run-up and deposits going up. So they can map these deposits island after island. And the next set is 4 islands to the west. And what you find in all these cases are nice tsunami sand going way up to 20 to 30 meter elevation above the mean sea level. And they're nice coherent layers, so they can carefully date them. And of course, they see older deposits that will tell you about older tsunamis, and I'll talk about those next. This summarizes the observations that the geologists made, okay? So the aftershock zone from seismology is this kind of pink zone, but what the geologists are seeing are these huge run-ups in the eastern part, where all the seismic and tsunami model had run up over here up 4 to 9 meters, was consistent with the magnitude of the slip that they had there, which was on the order of 4 to 5 meters of slip on the megathrust. Okay, so either there was a mystery event that wasn't associated with the 1957 rupture, or more likely, 1957 rupture has really been underestimated. So we started with these models, the available models from 1994, and these were the standard for the next 20 years, right? So pretty much anything you would find. If you compute the tsunami using modern codes for those, you can see for the tsunami model and the seismic model, they produce radiation. It goes to west of Hawaii, which is over here. And they don't produce much in the eastern part, as you would expect, of the Aleutians. In fact, these are the predictions from those models, from the tsunami model. Here where the observations of run-up were, here's where the predicted run-up is. It's right on the coast. It's a meter high. It's one of the most egregious failures to predict data that you can imagine. It just doesn't even come close. It's not halfway there. It's 10% of the way there. And the same in Umnak Island as well. The predictions for the seismic model are equally bad. I'm not ragging on anybody. It's just something was really missed because they were not using the tsunami observations. They didn't have the tsunami run-up observations locally. They did ignore the fact that there was a tsunami of 16 meters high on Kauai, and there was run-up measurements all along the Hawaiian Islands, which are much bigger than would be predicted by either of those models. It was just not, they didn't pay attention to it, or they didn't trust the run-up modeling, but those models failed to predict any of the tsunami observations to the south. What we did was start with the seismic model. I don't trust the tsunami model from Johnson and Satake because we're going to model the tsunami, remodel it. The seismic, yeah, there was something, the significant slip in the west, that's probably okay, but in the eastern part of the fault, all of these grids, the 7 eastern, or 600 kilometers of eastern part of the rupture model, we find that in order to model the run-up, you're going to have to put very large slip at shallow depth. We know the depth has to be shallow because we will simultaneously model observations in the Aleutians and in Hawaii. And in order to match them equally well, you cannot do it with deeper slip because deeper slip, you'll produce uplift under the shallower water, and it will de-shoal as it goes to Hawaii. You can't get the amplitudes as big as you need in Hawaii, even if you manage to fit the amplitudes in the Aleutians. So it's a balancing act of where the slip is. And we find that the most efficient way to account for the observations in the eastern Aleutians and Hawaii is to make shallow slip along here. And this is going to be the preferred model. And these are the slip magnitudes. It's not trivial. We've got 26 meters of slip, between 12 and 26 meters of slip, over 600 kilometers, totally missed in the earlier models. Okay, so it's a substantial revision of existing kind of paradigm earthquake. Tsunami calculations for the preferred model are shown in this plot. And what you see, the large amount of slip in the west, or the small amount in the west predicts moderate local effects. The big slip in the east is going to produce very strong waves, and those are going to hit right on Hawaii very strongly and give us the opportunity to account for big run-up in the Aleutians, big run-up in Hawaii. It's accounted for by a narrow strip of uplift. It's similar to tsunami earthquake. It's the upper 30 kilometers of the megathrust, which is experiencing this tens of meters of slip, and it produces a ridge that was very similar to what happened for Tohoku, a ridge of very narrow, high uplifted sea level that then propagates toward land, and it propagates toward the deep sea. Using non-hydrostatic codes, it's important because the uplift at the trench, as it propagates toward the land, will interact with the reverberation of the downdrop seaward or landward, and it will constructively interfere to give you the necessary amount of run-up. So you have to do non-hydrostatic modeling. And at the workshop, everybody was saying, yeah, we have to do non-hydrostatic modeling. So the community has come around to how important this is. When you do that, these are predictions for the successful model that show now, yeah, we can get inundations all the way up to where the logs were, up 30 meters. We can predict all the tsunami sand deposits up to high level for the Stardust and the Umnak Island. Also, this is the island to the west where you get run up. I'm sorry. This is Kauai. This is the island to the west. For Mountain Island, this is run up on the south side of the island. We can't quite match the run up on the north side because the bathymetry is not good. The waves have to wrap around the islands. But the south side is exposed and has these 15, 16 meter run-ups. It's consistently estimated by our slip model with this large shallow slip in the eastern part of the fault. Along Kauai, the biggest slip in Hawaii, run-up in Hawaii was 16 meters. At that point, we can't quite model. It's a local effect. The detailed bathymetry offshore might not be adequately expressed. But the 10 meters along all of the northern coast of Kauai and coming to the eastern coast of Kauai, we can model very adequately. And in the bays, in these bays, there were inundation deposits were measured, and we can match those as well. And this is going all the way to the Big Island, where the waves might overpredict by a meter some of the observations. Of course, it's a little bit tricky because in the past 50, 60 years, sedimentation has been occurring, so the precise depth of the bathymetry in 57 versus now, we try to make corrections for, but it's difficult. So with this 600 kilometer long shallow rupture in the east, it's important when you're making models of inundation and you're transporting logs, big trees, that you have a deep enough water. So you also need to calculate the flow depth, how thick the water layer is, can it be transporting trees? And along the Aleutians, it needs to be a couple of meters of water can transport the trees. This has been really calibrated by the Tohoku earthquake to see how the debris dropped out when you had varying amounts of water depth. And so the calculations have sufficient flow depth in order to account for the observations. This shows inundations in Oahu, and this is on the Big Island, Hawaii. These are local observations where they went in, they did core holes, and they found the inundation from 57, and we can match those data. To get sufficient strength or depth of water to transport sand in Hawaii, you probably have to have more like 4 meters of water depth. And this is because there's a very different kind of hardness to the sands off of Hawaii than you have in Alaska. It's been calibrated, so we paid attention to how deep the water is as well as the peak runout. The bottom line is this is the revised version of 1957 earthquake. Still has slip in the west, modest amounts of slip, can produce 9 meters of run up here, 4 meters here, but along 600 kilometers, you have very big slip. We believe it's coseismic. It's not a separate event or a slow event on a different day because the full model matches the tide gauge data. I didn't really emphasize that. I felt a little pressed for time. So this is the coseismic 1957 model revision. And I've never been involved in revising an old earthquake slip distribution that had such a dramatic change. So it's interesting. Totally attributable to the value of our friendly tsunami waves. It didn't hurt anybody in the Aleutians, nobody who lives there. There were negative impacts in Hawaii from the big waves that hit there. Okay, so that gives us these two events, 2020, 2021, and 1957. Aleutian events have benefited from recordings of the tsunami waves. I'll finish with going back in time in the 1957 zone, because as I said, they went to the islands in Umnak and Sadaka. They trenched, so they made shallow core holes. They dug trenches, they core holed, they looked at exposures in the sands, and they mapped out stratigraphic structures. This shallowest one is 1957. And they can see older continuous tsunami deposits going up to various elevations. They see 6 of them in each of those regions. Now, the most recent 4 are pretty coherent, can be accurately dated, and are not too disturbed by subsequent events. And so you can see stratigraphically these features and correlate them core hole to core hole and get a pretty good sequence of events. The yellow events are large earthquake tsunami deposits. And there are volcanic eruption flows that help to date them. But the dating of the tsunami sands themselves is always problematic, has some uncertainty. So you end up with little distribution functions from Driftwood Bay on Umnak Island is in green, Stardust Bay in blue, and these are as a function of time. So 1957 is over here. Everything well resolved temporally there, mainly because of cesium from nuclear explosions that started in the late 40s. They kind of know when that ended and can identify the 57 events very well. We didn't have nuclear explosions going on back here, so it's really geologic analyses, oxygen, various isotopes that they can use to get the estimates, these kind of distribution functions for past events. But you can see events that were observed on both Driftwood and Stardust, or just on Driftwood, and back through time, with kind of broad uncertainties in age, on the order of plus or minus 50 kilometers. So we'll call them by their century in which they occurred, because it's not precise as to whether this is one event or two events that are close together. It's just the event that made these deposits within a 100-year period. So this summarizes the four recent events: 1957 over here, an event in the 18th century, an event in the 15th century, an event in the 14th century. Not observed at all sites. Only in Hawaii, the only one that's observed is the 14th century event. So that's got to be a big enough event, like 1957, to get big enough inundation in Hawaii to bring in sands, 4-meter deep water necessary, penetrating into the drainage basins that they court for you to have a record of those events. These other events did not, the 15th century and 18th century events did not produce large enough waves in Hawaii. Doesn't mean there was zero, but it means that it was not big enough to make a deposit. So we modeled the available data set, again using the strategy. We modeled the recordings and the illusions, how big it was and what islands saw it or didn't see it, in order to get the length along strike. The magnitude of the run-up tells you pretty much the slip. The observation of, is it in the illusions, is it in Hawaii, gets you a position along dip, okay? If you see it in both, it's got to be shallow in order to get the strong enough wave to Hawaii. If you don't see it in Hawaii, it's likely deeper on the megathrust, and that will then not produce strong amplitudes in Hawaii because of deshoaling. And this is the fit to the 15th century event observed at Driftwood Bay and Stardust Bay. The observations are very similar to what we saw for 1957. So because of the tsunami now, we're able to extend the seismic, or the record of big earthquakes back. This is going to an event that is not really uniquely documented by the fur trappers that were out here. There's very little activity right in this particular area. And we find a model, which is that the rupture didn't happen shallow on the megathrust, or else it should have been seen in Hawaii, and it's not. So it's deeper on the megathrust, deeper than occurred in 1957. Nothing slipped this deep in 57. 15th century, 30 meters of slip near the trench, in the same area that slipped 26 meters in 1957. Okay, this is 15th century. It's 5 centuries before. It's re-rupturing the same shallow part, like a tsunami earthquake, very near the trench on the crust mantle, or on the crust slab contact. The 14th century is all rupturing deep on the fault. It's big enough to produce the Aleutians arrival and some modest arrivals across Hawaii. So we're backing out slip distributions for historic events in the eastern part of the 1957 zone. You can demonstrate the fitting of the data in the 18th century. The very low inundations cannot produce deposits for the 18th and 15th. The 14th century, there's sufficient flow depth to account for the observed sands deposited in the cores in the Hawaii bays. Okay. So this compares the model. This is our 57 kind of correction to the available 1957 slip models. This is where it slipped in the 18th century, deeper. So this is all shallow, very large slip. This is deep, very large slip. Still a big slip. It's a big earthquake. It's a magnitude 8 size earthquake, but the slip is not going to the trench. So it's sort of complementary. It's filling in this particular square. 15th century, it overlaps, re-ruptures. The area that slipped 26 meters slipped something like 30 meters, 32 meters. And then the entire deeper region that did not slip in 57, along the entire length, 600 kilometers, we think ruptured in the 14th century event. Okay. So this summarizes all the models, the 2020, the 2021. 1957 is in this blue and the red area outlined in white. That's our adjustment to the 1957. And then we have our 18th century fault, our 15th century slip, which overlaps the 57 shallow rupture, and then a 14th century. They're just uniform squares. We don't have detailed space information, not like the kind of exquisite spatial temporal resolution that we get from modern finite fault inversion, because it's based on run-up with no timing information, no tide gauges. But something like that happened, and it happened in those portions of the trench. Oops. Okay, so in conclusion then, I hope while we all recognize the dangers of tsunamis, you now see, well, some of them are helpful and we can utilize their unique attributes. The principal one from the wave propagation point of view is their very slow velocities, much slower than seismic waves. This gives good spatial resolution. As long as you have the ability to predict the travel time through an accurate bathymetric model, it really has very little wiggle room. And so they have a tremendous asset for imaging of the source. Plus, they can be observed by run-up measurements over very extended distributed areas if you make the effort. So you really have to take the field surveys and the geologic sampling of historic events to exploit them to the maximum. But I think we've been able to do that. And if you want to see many more examples, take a look at the paper that Fabrizio and Stefano and I wrote. And it's just a panoply of many demonstrations of value added. So all your efforts here to develop capabilities to model and to analyze tsunamis is translating also into big impact on our ability to image important big sources so that we can do more detailed investigations of do slip patches re-rupture over time? Are they persistent? To understand the distribution of aftershocks and to evolve our understanding of the megathrust faulting. So thank you very much.
Thank you very much, Thorne, for your fantastic presentation. You have just commented on the superior NGV organizations, but we failed you with the batteries immediately. Sorry for that.
And that was filmed too. So.
Sorry about that. So I recall that people online can insert their questions through the YouTube channel. And Massimo has the first question.
Yeah, thanks, Thorne. Very stimulating. I have a couple of questions. The first is general on the dynamics of the tsunami quakes. Because if you have, which is the stress state of the subducting plate that justify the capability to concentrate the slip shallow or deeper during the cycle? So what happens dynamically?
It's not easy to answer because there's a lot of research going on to understand why the contact between the crust, the upper plate crust, and the slab may be differing from the contact between the upper plate mantle and the slab, which is what happens in going from the 57 event. All the rupture with large slip is along the crust slab contact. It's not necessarily, we don't know the slip velocity that was involved in this because we're measuring it with static deformation. It's not truly a tsunami earthquake which has particularly low rupture velocity. I think it does because it didn't produce big seismic waves that could be imaged in even the one record that they imaged. They couldn't pick up this deformation. So I think it is slow slip. So there's some different attribute. And in general, I believe the very large slip implies low rigidity in that shallow crust slab contact compared to the deeper mantle slab. It may be that the dynamics are strongly influenced by this long dip transition. In fact, when we look in most subduction zones, very few, only one instance where only the mantle ruptures in the mantle slab contact. So generally people argue, well, you've had serpentinization, the slab's bringing down fluids, it's weakened the deeper contact and put into stable sliding. Well, this has deep slip on that mantle slab contact. I don't think we know yet, and there's still a lot of uncertainty as to whether serpentinization is often invoked as a means of softening and making this depth-dependent variability. But now we're seeing exceptions to the dogma. So I think it's a little bit early. Maybe if we have a few more examples, we're going to be able to answer that question more definitively. Here we have a dearth of kind of kinematics even of the rupture. It's we just put in the slip because we know we have to have the slip of that magnitude in order to match the signals, but I don't know any more detail about that slip.
Yeah, because one of the comments that came in my mind looking these variable models would be how much the slip gradient would control the inversion. Because if we invert statically, we are essentially distributing slip amplitudes on a given grid size. But when you do something that is dynamically coherent, the gradient of slip, it is the state of stress, and therefore this variability should correspond. And my second question is more on the perhaps I was confused on the methodology, because at the beginning you said that you invert with classical, let's say, geophysical model, teleseismic and GPS, okay, and you have a source model. And therefore, with this slip model, you try iteratively to perturb the model in order to fit to the tides and the tsunami data.
Yes.
But now the question, and even changing the grid size, if I understand.
No, we did not change the grid size. We simply suppressed slip in rows.
Okay. And therefore, the question is here, because these inversions are static, therefore you check afterward if the perturbed model still fits the teleseismic and GPS data. But do you have a test in a tsunami where you have, for instance, seafloor observations in which you can fit a posteriori them to demonstrate that your iterative procedure managed the bias, for instance, within geometry and slip? For instance, Toku, no? Forget the seafloor observation. Forget, you simply do the teleseismic and the kinematic. You did the iteration with the tsunami data, and a posteriori you demonstrate that your refined model fits the seafloor observation, which are the only data that might constrain the slip gradient.
Yeah, but the procedure basically is iterative in the sense that we do a joint inversion of seismic and geodetic, and we make a forward prediction of the tsunami. So it's sort of a validation test, right, of that. Then we recognize deficiencies in the prediction of tsunami, so we adjust the model. We suppress slip in the shallow row. We redo the inversion of seismic and geodetic, and then do a forward prediction of the tsunami and compare, and say, have you improved? And if it's going in the right direction, we might take another row and suppress that. So in a sense, it's a sequence of inversion and forward prediction to validate the model. Now, on this trip, we've been discussing dealing with the problems of joint inversion, which we've done joint inversions before, but not in this region with a very flat, ocean, continental shelf, and not in the situation where maybe islands that produce nonlinearity in the local excitation of the tsunami. We can probably deal with those problems, but we may have to have different grid dimensions for the tsunami in the joint inversion. There are technical ways to do it, I think. In that case, we'd be able to do everything inverted together and see, are we getting the same type of models? Did we converge to reasonable models? Which I think we did, because it does fit. So it will be within the distribution of viable models. But it's a cleaner thing. You're not uncomfortable. It's a familiar thing to do. But at least, this was COVID times, and we just did what we could do fairly conveniently. And it worked very cleanly because of this high sensitivity to proximity to the continental break. And all we had to do was pull back from that, because that produces nonlinear enhancement of the tsunami. So in a sense, we're using the tsunami observations to validate a sequence of kind of tighter and tighter inversions of seismic and geodetic data. Is it clear how we're doing that? Yeah, okay.
Hi, Thorne. Is it working?
I think.
Thank you very much for the talk, which I really enjoyed the story all behind, how you went back in time and, to figure out earthquakes that had not been found ever before. I have one question about the 1957 and the actual inundation data that you use in order to constrain the fault model. How do you put them in the actual inversion? I mean, do you put it like a kind of soft conditioning, or I'm not sure I've understood that.
Okay, in 1957, we never do inversion. It was forward modeling through suites of models with slip at different depths with different magnitude, and it's a search. But we quickly realized we weren't even close unless we put the slip shallow to be able to match Aleutian and Hawaii simultaneously. So it's a sequence of forward predictions there, because it's not a well-conditioned problem for doing inversion. You could try, but I don't see any particular value in it. It's very constructional. So in that sense, 57 is very different than what we could do with 2020 and 2021 with lots of, high quality time information and constraint. But in 57, we do have the tide gauge data that gives us temporal fit. I skipped over it, and I probably shouldn't have. If I could quickly go back to that. These were the fits that we achieved to the tide gauge on the right for our favored model, is I think the one in red. And the black is the tide gauge. So the temporal information for the model that includes this eastern 600 kilometers of shallow slip is that we made it slip instantaneously. We don't know the kinematics. It clearly was rupturing over some time, but probably small relative to the wavelengths that we're getting this peak run up from. And those are better fits than from the earlier models. So we're actually confident that making this coseismic with the 57 actually does fit what limited temporal information we have for that event. But it's still not inversion, it's forward modeling construction because of the limitations of the different data sets. But that, there have been improvements in the codes, and we think there were kind of, even though they got better fits originally in Johnson and Satake, that there was insufficient quality of code for the modeling, whereas using a good non-hydrostatic code, we're able to fit the signals much better with a much different and more complicated fault. So it's forward modeling. Hard to establish what is the non-uniqueness, hard to establish the uncertainties other than empirically, stepping through a bunch of models, which is what we did. But that's the nature of these older data sets. You're just going to have to tolerate less formality.
Thank you.
Hi, thanks for the talk.
Thank you.
In the cases that you didn't use tsunami as external validation and you did a joint inversion, did you have a special strategy for the weight? How would you weight?
Yeah, we spent a lot of time, say for the 2010 Mentawai and also for the Maule earthquake, in trying to balance the information from the different data sets. It's different for every event, so it takes a lot of time to do it. In Maule, we had some nearby GPS, continuous GPS, and we had teleseismic, and we had tsunami from 4 stations. In Maule, you have all the INSAR and all these other data sets, and you're trying to weight them each appropriately to not dominate the solution, but to give where they're complementary information, merge it constructively without just canceling out in any way. So strategy-wise, it was largely searches over individual variance reduction of parameters as a function of how much we weight different data sets. You can use information criteria to try and optimize the weights, but we found that was as bottomless a pit as doing large searches. So in practice, it was searching over, it'd take a day to explore the relative weights and the outputs from that, because the inversions themselves are fast. It's just a question of how big of a search of relative weights you want to make. What we found for the smaller event for the 2010 Mentawai is that we had to vary the subfault size as well to explore the nonlinearity and the precision of the Green's functions for the tsunami, and trying to adjust the corresponding subgrid size for the seismic and geodetic inversions to have a simple compatible model. So you have to be careful because of the sensitivity, the size of the seafloor patch that you, or the fault patch that you're deforming seafloor, influences how water moves horizontally and diminishes the uplifted sea surface elevation. Those kind of considerations have to be attended to. But it was sort of brute force because it was the first time we'd done joint inversions, and I think that's what you kind of have to go through, is that learning curve. I don't have an automatic algorithm because it's going to be different for every event as to what data sets you have and what their mutual sensitivities and complementarity is, unfortunately.
And one more, how do you decide the size of the patch?
For the joint inversion problem, it was basically from exploring how accurately the Green's functions were produced for different size patches with the particular code we were using, which was NeoWave. So it's non-hydrostatic. It's accounting for water moving out as the sea level uplifts. But we were trying to reconcile it with the seismic data. So it ended up being like 8-kilometer patches, and then it didn't matter if we went bigger, it was okay. But if you go smaller, you could have some problem. It's just an instability in the Green's function calculation.
So very exciting talk, and my question is about the topography of the continental shelf, and if this could be the effect of repeated megathrust through time, so that uplift, or a cause of the limitation of the rupture in, what do you think?
Yeah, it's an interesting question. I mean, Alaska is continental, but as you're going out the Alaska Peninsula, it's slowly transitioning to island arc, and it's island arc by the 1957 zone. The flatness of it, there have been some people exploring this issue of why it's so flat and where the deformation zone is, and they would argue that the strong coupling should be seaward of the flat continental shelf. These arguments have been made, which would put it all in the area up dip of where all the slip is. So there's a problem with those arguments, and they say, well, it's just different in Alaska because it's unusually flat, but I don't quite understand that. But I haven't paid too much attention to the feedback between the flatness of the shelf and the deeper reflectivity, because along the Alaska Peninsula, there are many terrains have been laterally mobilized, kind of slivers that have moved southwestward, and these terrains are imbricated along the arc. So it's not kind of massive uniform continental shelf. It's a bunch of accreted terrains that have been squeezed west. So it probably doesn't have as much integrity as, the fact that it's so flat is probably more from the effect of climate change. Of 100 meters to get you to where all this was exposed. And so I suspect that's more of a feedback than a feedback on the subduction zone. But again, they don't know the cause of the broadening of the reflection from the megathrust either. People argue it's accumulation of damage zone or some multiple shear surfaces, but why there was such an abrupt transition to a very sharp zone, I have not heard a good explanation for that. It's sharp, but it's rough. So I think it could support some strain, and it appears to. One thing I didn't mention is that there is seafloor geodesy seaward of the 2020 and the 2021 event. And they both show no coseismic slip, for so good, on the Connell slope. And they also are seeing large amounts of afterslip. So the shallow, very sharp part, well-defined megathrust, where you might have thought that's where the slip is going to be, it didn't slip. It's having afterslip. So it's kind of counterintuitive to me. But if you have ideas, I'd love to hear it because I don't quite understand it.
Thanks for the very brilliant presentation. Your reconstruction of the 1957 event with the sea level data made me think of a general problem that I want to ask you your opinion, that sometimes when there are sea level data that are not explained after an earthquake of a certain magnitude, it is often invoked some mechanism of landslides adding, sometimes with evidence, sometimes with no evidence of an offshore landslide. So you know about Palu earthquake, even the Messina 1908, and many others. So what's your opinion on this general approach?
Well, I'm just an observer of it, but over the years I've noticed that tsunami modelers are in two camps. There are people that want everything to be a landslide. There are people that want everything to be an earthquake faulting, and sometimes they strongly disagree over the same data. So my own experience is mostly with earthquakes, though I learned a lot about slumping events. But I would say that it's like for the 1946 event, just to the east of 57, we're trying to model it with just faulting to see how far we can go. And I think we're falling a bit short. So I'm willing to admit there probably is an additional source because our best effort so far has not managed to completely explain the data. The 1957 zone, when I gave a talk on that event at Caltech, and were people saying, well, it's just landslides. And I was like, well, maybe, but then you have to have landslides over 600 kilometers all at the same time. But you know there was a big earthquake and there's aftershocks through the whole area. So for me, because I could model the slip distribution, I tend to explore that parameter space. Of course, it's possible that there was triggered multiple landslides that were producing very big waves, but my knee-jerk reaction is not to make that model. Other people might explore that, and I'd be interested to see if you can reconcile the Hawaii data and the data in the Aleutians. But it's difficult because the landslides typically will go toward the sea, and what you need is big run-up in the opposite direction. And so it's challenging to account for a 30-meter run-up, just as it has been for 1946. They have 45-meter run-up, but it's I think it's in that case going to take a combination of earthquake and landslide to account for the captive and the lighthouse observation.
So I take advantage of having the microphone and insert a comment before Paolo Marco. Thank you, Paolo. Have you considered the possibility of inelastic deformation contributing to the uplift there? So, which would in turn imply a different slip distribution.
For 57, so these large.
For example, in this type of situation, that might alter a little bit the very narrow pattern that you have for the very shallow patches.
There's a similar kind of bifurcation of communities that like elastic media and like inelastic media as to the relative role of deformation in the upper plate, which can push up and deform the seafloor and make excitation. I cannot rule that out. What we did was demonstrate the viability of slip. It's a demonstration of existence. That type of model can match the data. I cannot preclude the idea that there is large anelastic deformation that's involved rather than slip. But for Tohoku, I mean, we know that even though you had 30 meters of slip down dip and you have 50 or 60 meters slip shallow, there was no need for anelastic deformation because they can see the offset of the seafloor, 50 to 60 meters. Where when you go to the north, people like Ma have argued that there is it plastically failed and there was almost no slip on the megathrust. But in order to drive plastic failure, it seems like you have to have strong stresses applied, and there's no way to account for them. It'd be the same in the 57. No down dip slip would mean you don't have the deformational stresses to drive the plastic failure. So why would it fail? But, I'm obviously somebody who's got the first reaction is, can I explain this by faulting? that's my bias. I acknowledge that.
Fair enough, I would say.
Hello, Thorne. Thanks for your very stimulating talk. I'm a geologist working on tsunami deposits.
Yeah, my heroes.
And so in this sense, I really love the effort you did in working on the historical data, run-up aids, inundation distances, flow depth, derived from tsunami data, actually. And the idea to derive the distribution of sleep, for me, is very interesting, because usually tsunami data are used for the recurrence at the site or a maximum inundation distance in general. And so the effort you are taking on is very, very interesting. And I hope that also in the Mediterranean area, even if we have a, let's say, lower magnitude event, at least for the largest one, there will be in the future the effort to incorporate in the modeling the tsunami data. In particular, because we have a very nice record for some large events, let's say magnitude 8 at least, like the 365 or the 1303, and along the subduction zone of Greece, where we may have enough data to try to combine them in order to drive a different sleep distribution with respect to the past. The only comment I want to make as a geologist is, please don't forget the fact that all what geologists can give is a minimum value.
Okay.
In terms of fitting the run-up rate or the inundation distance, is good, it's perfect. But it is always a minimum value, because some of the record has been obviously erased in some way or can be not found, both in terms of recurrence and distances. Thanks so much.
Fair enough. That's a good comment. But that's also why we looked at the flow depth. And we made sure that the flow depths were sufficient where we had the deposits, that it was viable that you could do the transport of sand or of logs or whatever. And the inundations then go beyond where we have actual data. But we were trying to respect that recognition that it is a minimum, but it's a minimum that we have a little bit of guidance on how deep the water has to be at that point, and it will go further. But yeah, I think Mediterranean there's enough coastlines around that you could probably do what we were doing with Hawaii versus Aleutians. It's a long distance, but having more than one observation. If it's just the Aleutians, very non-unique to figure out the slip. When you have multiple sites, you start to see the sensitivity, especially to a long dip placement, as necessary to reconcile the observations in different positions. So if you have good dating on sites that are on the north and the south and coast of the Mediterranean, the slip inversions will be better posed. So yeah, I'd say that the work that was done in Singapore, Kerry C's efforts to look at paleo events and to map them into slip distributions relative to recent events predates our work on 57. It was in the same spirit, and it was very transformative to have those models.
Thank you, Thor. They tell me we should wrap up, so we thank you very much for your talk, for these days of exchange together. And
well, thank you for having me participate. I've really enjoyed it.
Thank you very much.
Thanks again. Thanks, Tom. Thanks, Thorne, and to give us this opportunity. And now we have a lighter refreshment, just